I didn't choose it. It got glued on my presentation. Yeah, you do. We'll get back to this one. So I'm Yoav Murag. I've been with Zerto for quite a while now, almost more than 7 years, actually. Working most of the time, actually coding the ZVM, which is the process at the heart of our product, as most of you know it. And this session is about ZVM internals. This is what we'll be speaking about today. And the reason we'll be speaking about it is because I was asked to do this. And I was asked to do this because last year, two of my colleagues did a similar session at ZertoCon, which was successful. And the concept for their session was the car versus the engine, right? I started by stealing their presentation and looking at this concept, but it didn't quite fit for me. First thing, I'm not sure. The idea was that Zerto is the car that you are driving, and we are going to show you the internals under the hood, right? But Zerto is not really the car that you want to be driving, right? If you're an airline, the car that you should be driving is your ticketing application or whatever. Whatever your business, that's your car. DR is not the thing that you want to mess with. We want to be behind the scenes as much as we can. So this one goes away. And we're left with the engine. Now, the engine is a pretty good metaphor for the ZVM because it really does a lot of things, and it's a really powerful and a good engine, but it's also quite complex. And the things about engines, let's get back to the title I've got. Anybody knows where did they get it from? What's the reference to? Song, right? What's the name of the song? She sings My Tractor Sexy, right? You can hear from my accent, I'm not from around here. And I'm no expert in country music, Johnny Cash excluded. But that's the title of the song, so I Googled up the song and I've heard it. It's a really funny song. She sings My Tractor Sexy. And I happen to own a tractor, right? That's my tractor. I actually own it. I bought it with a couple of friends and we had it repaired. And we use it to drive the kids around every now and then. And the thing with engines is that if we start speaking about the engine, it's a lot of parts and they're doing different things and it gets very complex. So scratch the engine, scratch the car. I'll give you another story. Right, and I hope you like this story because this story begins with you, the customers, and you are the kings in this story because the customer and king is a king. And what's a king? A king owns stuff, right? He owns the data center, he owns the application. A king gets things done, right? He has a virtual machine, he has citizen doing stuff for him, doing useful stuff for him that he can store in his storage. He doesn't do things by his own, he has other people doing it. And we are one of your citizens. We happen to be a first-ranking citizen. We have more privileges than most of the citizens that hang around your data center, your kingdom. And the service that we provide you with is protection, right? So that's the concept for my presentation. All right. So let's see how it goes. I'll be going through things in a chronological order. I'll start by the setup phase, how we configure the environment, how we install stuff, how we configure a VPG. Then I'll be speaking about the sunny days, the everyday replication state, the steady state. And finally, I'll be getting to recovery. In the unlikely event that we'll have some time left, I might be able to cover, I have a few slides about LTR and JFLR as well. And we might get there, probably not. Maybe another slide about CSPs. And as I'll be going through these subjects, I'll be taking a look at two different things. I'll focus on two different aspects. First thing is all the stuff that we do in your kingdom, all the resources, all the virtual machine, all the storage that we use on your environment. I try to put a special focus on that, explain why we use the resources, what we use them for, why we attach and detach volumes to all kinds of VMs, why we lock some of the VMs, why we unlock them, when we unlock them, and all that stuff. So I try to explain this, that the king might be thinking. And the other thing I focused on is the things that we do when you're not looking, right? Because we want to be in a very little interaction with you as users. We don't want you to see our GUI too often, right? We want to work behind the scenes and do the protection for you. But we do a lot of things behind the scenes. And I try to take a special focus on these things. So let's start with the setup. And it starts with a story about a king that had a kingdom, right? And he has a data center, his hypervisor at the heart of the kingdom. And he has a lot of hosts that can host many virtual machines. These are the citizens that produce valuable resources for the king, right? Wheat and bread and whatever, and these resources are stored on the storage on the site. The thing is that every now and then a dragon comes out and burns the kingdom, right? And burns the data center and burns the hypervisor and burns the poor citizens and the resources, of course, which is all the king cares for. So we have a plan, and the king happens to have another castle up there in the mountains. It doesn't have to be as big as the other one. This one has only a single host, but it's a secure place, it's another place, and we can call upon our knight, give him the keys, deploy the ZVM on both castles, on both ends, have the ZVM deploy VRAs, which are designated VMs that we put in each and every host, both on the recovery and the protected site, create some sort of designated storage on the recovery site, copy the resources. This is easier done in fairy tales and digital media than in real life because you can't replicate bread as easy. But it happens to work for us because we are in digital media. So we replicate the stuff to the other site, and we have it protected in case the dragon comes again. One thing you should notice is that we do not move the VMs themselves. We only move the storage to the recovery site. If the dragon will come, we'll pop up new VMs on the recovery site, attach them to the storage, and everything's good for the king. So before I continue, I'll take a brief look at the terms we'll be using and the terms we will not be using. So the hypervisor or data center appears as a castle. The host appears as a village. The internet, the forest that no kid is allowed to wander into alone, and some grown up not as well, appears as a forest. The cities are the VMs that run your workloads. The storage appears as a field. The volumes appear as a field. And the actual data appears as resources. That's the language we'll be using. I also denote the designated Zerto VMs with all sorts of constructs that we use, and the designated Zerto storage with chests, right? And any Zerto process will appear as a knight. So that's our language. One aspect of the system that I cut out for simplicity is the data store aspect. So that's out of there is no image for that, and I will not relate to the types of storage that we use. So once we deploy the ZVMs on both sides, we need to have them communicate with each other. And since they communicate via the internet, we need to deploy a safe route through the internet. And this is the VPN that we use. The VPN is used for two different channels. One is the control channel. It's a single channel between the protected ZVM and the recovery ZVM, right? Having one ZVM connect to another is called pairing. When the pairing is done, the ZVM notify the VRAs on both sides of the existence of the other side, and a designated data channel is created between every VRA on the protected side and every VRA on the recovery side. It might not be open from the start, we may, but potentially that's a full digraph between all the VRAs on both sides, right? If you have VPGs between each and every VRA, we'll have as many channels. So let's speak a little bit about topology. We already saw that we can replicate from one site to another, but there is no protected and recovery site. There is a protected VPG and recovery VPG, but there is no site type. Both sites are equal in that term. You can replicate some VMs from site A to site B, and at the same time replicate other VMs and other VPG from site B to site A, so replication is symmetric. However, the hypervisors are not symmetric, right? We have all sorts of hypervisor that present different sort of castles that we can replicate to. In this case, we see a VMware site replicated into Hyper-V site and backwards. And there are also the castles up there in the clouds, the public clouds, the AWS and the Azure that we can replicate to. Right. So another thing we can do, we can replicate within the same site, right? That's called the local replication. We can replicate a VM from one host to another, and in case the first host is down, we can fail over to the other host. Another feature that we have, we can replicate the same VM to two different sites, right? This is called one-to-many. So that's the topology we support. Let's take a quick view of our heroes so far. So we have the ZVM. We have a single ZVM per data center, per hypervisor, and it is at the heart of the system, right? Then we have the VRA. The VRA is responsible to actually replicating the data from one site to another. One thing I need to tell you about the VRA is that it has no persistent state. It has no memory of its own. So the ZVM is responsible to giving all the information it needs to work. You can restart the VRA and it will synchronize. The ZVM will synchronize it and let him know everything it needs to operate. And for the rest of the presentation, we'll be focusing on the processes that happens here in the ZVM. Right, so what are the roles of the ZVM? The first role is to communicate with the hypervisor, to collect information from the hypervisor, and to do operation on the hypervisor, such as create VM, move VM. Another role is to communicate with the peer ZVMs, right? It can query the peer ZVM for information. It can give him commands to execute. And that's a peer-to-peer relation. There is no one ZVM that is superior to the other one. Okay, the other role of the ZVM is to communicate with the user, to get commands from the user, to report problems, to report statistics, and to report the state. The ZVM has persistent storage, right? If you restart the ZVM, it will recreate your replication at the same point that you were before. So it needs to keep a persistent storage of the state. It initiates some operation periodically, so it needs to have some sort of timers to initiate operations without any user intervention. So that's another role of the ZVM. The most important activity that it needs to initiate is inserting the checkpoints, and we'll be taking a deeper look on this one later on. Then it deploys all sorts of VMs on the recovery and protected side. The most important one is the VRA, of course. And finally, it collects some analytics info that we need in order to improve and to analyze problem for our own analytics. Right, so we already saw that we support multiple hypervisor, multiple different environments. But one important thing we need to understand is that we use the same product for all these environments. So it's the same code, the same compiled code that is running on all these environments. So if we were to look on each and every of these guys and send him to medical examination, we will see, right, that he has a very specialized tools for each environment. We know the environments. We do some very specialized stuff for AWS, such as deploying workers. We do other stuff that is specialized for SCVMM and Hyper-V, and we do a whole lot of specialized stuff for VMware, but that's different platforms. At the heart of things, it's the same heart. And that's a very important concept for us in dev. That's actually, as Zerto grew up, and I've been there, that's the single most important reorganization we did internally in the ZVM group, was to split the core and the platform teams, because this allows us to add platforms and enjoy all the previous features we had, because it's the same code. And this allows ZVMs on different platforms to easily talk and communicate with each other with few bugs and a whole lot easier maintainability. So this allows us to grow, right? So we had the sites connected, we deployed the VRAs, and now we need to create what is called replication, right? So before you know this process, the title for the slide reads configure VPG, but you don't see a command configure VPG in your GUI, right? You have two different commands. You have create VPG and you have edit VPG. But under the hood, it's the very same process. It's the same process. So I'll be talking about this process. And this process starts before the user even starts to interact with the system. We have the ZVM reports to each other all the time the different resources that are available for recovery, what hosts there are on the recovery site, what hosts have VRAs. And we have the other ZVMs report what potential resources can be protected. So by the time you come to the system and interact with the GUI, we are already prepared to give you all the information you need. We don't have to go and make complex queries, right? We can do it fast for you. And as much as we like to create VPGs on our own and save you the trouble of doing so, we can't. First thing is, we need to know which VMs to protect, right? Because some VMs may not be important enough for DR. And the other thing, we need you to tell us which VMs depend on each other, right? Because if you have a database server, that is a farmer producing wheat databases, and another application server, web application server, doing bread, we need to know that they depend on each other and they need to be protected together, right? So we need this information from you. And the information that you provide us when you configure a VPG, I'd like to think about it as a tic-tac-toe matrix, 3 by 3. Why? Because on the time level, you give us a configuration for now, for the creation of the VPG. For example, which host to replicate to, which data store to use. You give us settings that will be used during steady state. How much journal space can we use? How much journal history do we need to keep? And you give us settings that we'll only use when you fail over or fail over test, such as what network to use, right? So we have these 3 dimensions. This is 3 time. And on the other dimension, we have the VPG level that contains the VMs, and each VMs contain the volume level, right? And these are the settings that you give us. Once you give us these settings, we create the resources on the recovery site that we need. And we need to make each and every VRA on both the recovery site and the protected site aware of the volumes that you need to protect. One thing that you should note about the VRA is that they are only aware of the volume level. They are not aware of the VM or the VPG level in general, right? And another thing that we may be getting into later on is, although the VMs reside on the lower village, over there, we notify the protected VRA of the other village as well, that these volumes are protected. And I'll be getting to why we do this later on. Okay, so once we have the VRAs aware of the replication, and once we have the resources created on the recovery site, this state is called replication. And once we have this state, we keep it persisted in both sides. And this is a configured VPG that is active. It might not be synced yet, it might not have any history, but this is a configured VPG. So how do we get to this state? We need to do this transactionally. We don't want to get into a half state where the VRAs think there is a replication, but on the other side, there are no resources to receive the IOs, right? And we don't want to, on the other hand, we don't want to create the resources but not use them, to leak resources on your environment. So we either do the entire replication state or we don't do any of it. And how we do this? We open a thing called a transaction. One of the ZVMs is in charge of running the transaction, but the transaction itself may perform operation on both sides. So that's a two-sided transaction. And everything that is done is logged in the transaction. So if we create a volume on the recovery side, we write down we created this volume. If we notify the VRA, we write down we notify the VRA on the protected side, and we write down we notify the VRA on the recovery side. And only once everything has been done successfully can we persist the state of the replication in both sides and end the transaction. Unfortunately, it so happens that transaction can fail. Things can go wrong. And another problem is that sometimes it takes a lot of time to do the operation, so we don't fail very fast. So having these two problems of failures and running slowly together can be very bad. We want to prevent that. For example, if you configure a VPG, but you don't have enough storage space on the recovery side, we don't want to drag you through the whole process just to say at the end that you don't have enough process, right? So before we start the transaction, we do a lot of validations. And we do the validations on both sides to save you the trouble. Even after we did all the validation, things can go wrong. Stuff that was correct by the time of the validation can no longer be correct. I'll give an example. Imagine that we created the volumes on the recovery side. We went on to notify the VRA on the protected side, but by the time we got there, the host was down. This is out of our control, right? We cannot notify the VRA if the host is down. But we already created the volume on the recovery side. We want to undo that. So we go up the transaction, and we undo anything that we did so far. And another thing I want to tell you about the transaction is that they are persisted on the ZVM, because the failure may have been that the ZVM itself failed. And the first thing the ZVM needs to do when it rises back up again is to undo all the transaction that it did by the time it failed, right? There, we throw away the resource, and we got back to a clean state. So let's take a deeper look on the resources that we have on the recovery side. So far, I presented them as watchtowers and chests. The watchtower is the VRA VM. Now, this is a slightly confusing concept because the VRA is both a VM and a process that is running on this VM. So a lot of time we get support cases and they say the VRA is down, but it's not clear. And sometimes you don't know whether the VM itself is shut down or the process is unreachable for some reason. And that's a bit confusing, so you need to speak about the VRA VM and the VRA process running on top of it. The other resource that we have is called a mirror. A mirror is actually a single volume that has the same size as the protected side volume and has an image of the protected side volume, right? That's simple. And the other main resource that we keep is the journal, right? So the journal is actually a sort of a time-based list of changes that were made to the disk on the protected side. And if the farmer on the protected side replaces a little bit of his data from wheat to carrots, say, we list that down in the journal, right? And as the journal grows, We also insert checkpoints into the journal every now and then. We'll be speaking about this. And as the journal grows, we may allocate more volumes to grow it, right? So the journal is not a single volume like the mirror. And there is a single journal per VM. So if the VM has a lot of disks, let's say 5 disks, it will have 5 mirrors, but only a single journal, right? But a single journal, it may take many volumes. You may see many volumes. Now, some of the terms I've used are more hypervisor-centric. It may look a little bit different on the clouds, on the public cloud, because we use cheaper storage such as a S3 for keeping the journal. But we still have a journal and we still have the mirrors. The concept still exists everywhere, right? Another thing that can happen in the hypervisor is that because we need all the different volumes we create attached to our own machines, sometimes we don't have enough space on this machine, on the VRA machines, to attach all the volumes. So we create empty machines that have no operating systems and no processes just to attach the extra volumes to. And these machines are called disk boxes, right? So that's another resource we create on your environment. And all these resources are locked. We try to prevent you from accidentally moving them where they shouldn't be. So a short recap before we get to steady state. We've been talking about core and platforms. We've been talking about reflection, the information we are collecting from the environment. And we've been talking about transactions, how we actually do the processes in the ZVM. So let's talk a little bit about steady state. The single most important process that happens during steady state is the replication itself. Now, the VRA are responsible for transferring the data over the data channel. But every now and then, the ZVM has to insert a checkpoint into that stream, into the stream of the data. So if you have your ZVM down, your VRAs may be up, they may be replicating data, but you have no checkpoints at that time. So you need your ZVM up all the time. It's part of the replication process. So once the ZVM declares the checkpoint, this checkpoint goes to 2 different places. It goes to the recovery ZVM that is now aware of this checkpoint as a potential checkpoint, and it goes to the protected VRA that inserts the checkpoints inside the data stream at the right place. So if the protected VM did another I/O after the checkpoint was taken, it will be after the checkpoint. And these things are sent over to the recovery site where they are persisted. And the process of receiving these over the network and persisting them on the disk is called hardening the checkpoint. Once the checkpoint is written on the journal, we can say this is a hardened checkpoint, and the VRA can report the checkpoint to the ZVM. And this is now considered a valid checkpoint you can fail over to. And the information about the checkpoint, which checkpoints are valid, is also persisted in the ZVM database. So this is the path that the checkpoint passes, right? So how do we get application-level consistency across multiple volumes or even across multiple VMs from that? Say we have 2 VMs in the VPG, and they did certain I/Os, and now the protected VM declared the checkpoint. The checkpoint is inserted into the protected journals, into the protected data stream, actually, in such a manner that it will not violate the disk images the VM saw at that time. And then we need to send the checkpoint to the recovery site. However, they may not arrive at the recovery site at the same time. And if they only arrived on the single journal, we cannot fail over to this checkpoint yet, because if we would get the bread, but not the wheat that is required for it, right? So we need to wait for the same checkpoint to arrive and be persisted on all journals before it's considered a valid checkpoint for this VPG. Right. So another thing that happens as we go through the replication is that we gather a lot of changes, right? So the first change that's occurred, it's written in the journal, and there's no problem. And then there is a checkpoint, and we're still good. But then there is another change that was done on the protected side, and we're out of space on the journal, right? So one thing we can do, we can just grow the journal, right? It's elastic. We can allocate another volume for the journal and grow it and put a tomato in the journal, and we're good. But at some point, we'll arrive to a setting that you provided us with that limits the amount of storage that we can use for that journal. Luckily enough, there's also another side to this. There is another setting you gave us that allows us to keep only a certain amount of history, only a certain amount of, not amount, actually to keep history only up to a certain time. So at some time, this checkpoint will not be required anymore, right? If it's 9 hours old and we only need 8 hours of history, we can throw away the checkpoint, and we can throw away anything that is older than the checkpoint, put it on the mirror, and we get more space on the journal, right? This process is called apply. Moving stuff from the journal to the mirror that we no longer need is called apply, and this happens all the time. And if we don't get more data, we might be able to free up some of the space we used for the journal as well. So another thing that happens during steady state is that sometimes the internet may be down and the sites become disconnected. Maybe the site themselves are down for some reason. And when they come back up again, each of them has its own copy of the persisted state of the VPGs. And they need to compare them. Why is that? How come things may have changed during that time? Because they were disconnected. So the thing is, there are some operations, the most important one is failover, that can happen while the sites were disconnected, right? So when we compare the VPG storage, we need to synchronize the protected site to the recovery site, which usually knows better, right? There are some exceptions to this, but usually the recovery site knows better, and we synchronize the state to the recovery site. Okay, another thing we need to look out for is events that can happen on the hypervisor. I'll give some examples and how we handle them. So the first event we need to look out for is a vMotion, right? A VM can move from one host to another. And at any given time, all the VRAs in the protected site are aware of the resources they need to protect, but only a single one is responsible to actually send in the data over to the recovery site. And we need to transfer this responsibility from one VRA to another. And it may take us some time to understand that the VM has moved, right? But once we know that, we tell the VRAs to transfer the responsibility. This is called ownership. And we tell the rightmost VRA, he is now responsible for sending the data over to the recovery site. The reason the VRA had to be aware of the data is that until we notified him of the ownership, he may have already seen some IOs done by this VM, and we cannot miss these IOs. Right, so another event is the disk resize, right? The VM may enlarge the disk, and we need, in that case, to tell the recovery site to enlarge the mirror to accommodate to the new size. Okay, so that's another event that we send over to the other side to do changes. Right. Okay, one last thing we'll be talking about on the steady state phase is alerts. There are a lot of alerts. I'll give one example, is ghost alerts. We're looking at the recovery site now, and we're looking at all the resources that we have there. And if we have one of the resources accidentally moved or deleted or whatever, we know it should be there because we have the VPG settings. We know we use this chest. We know we use this VRA. So we report a ghost alert, right? You know that? And the alert is also propagated to the other side, so no matter what GUI you are looking at, you'll be able to see these alerts. Okay, another thing is there is a resource that we use between the sites, and that's the network. But you own the network as well. It's not our network, and you may wish to use this network for your own needs. So we need to limit the amount of network, the amount of bandwidth that we use. So that's another configuration you can give us. And if you give us a limit, we enforce this limit on the protected site, and we don't. The ZVM tells all the VRAs not to use too much bandwidth for replication. Right, so I've got another 10 minutes, they tell me, and I still need to go through recovery operations, so I'll be moving faster now. Recovery, right, that's what we're here for. There are several things that are common to all recovery operations. Right, the first thing we need from you for recovery is to know which VMs, which VPGs, and which checkpoints to fail over, right? And in order to create these VMs, we use the reflection. We keep some sort of data that allows us to reconstruct the VM on the recovery site. Once the VM is up, the first thing the VM will ask itself is, where is my data, right? So for hypervisor, we provide a VM with a thing called a view that is provided by the VRA. And the view is actually composed of both the mirror and the journal, right? So if the gray checkpoint was selected, we know we need to give all the information from the mirror overridden with the information from the journal until that checkpoint, which in this case would be the cart, right? So the view the VM will see will be the width from the mirror and the cart from the journal. On AWS and Azure, this works a little bit different, and we need to create the actual disk that contains the view in advance. This is why our RTO in public cloud is not as good as it is in the hypervisors. So what I want you to take away from this slide is that a view is an image of the disk composed from the mirror and the journal as seen at a specific checkpoint. We'll be using the view term later on as well. Another neat thing that we have is that the blueprints for the VM that we use are abstract, because imagine as long as we were in a Hyper-V only, VMware only environment, we're good, right? We can take the VM configuration and deploy another VM just like that. But if we want to fail over the VM from VMware to Hyper-V, we need to convert the reflection somehow, because the hosts are different and everything is different on that environment. So we need a two-way conversion between the formats. And this gets more complex because if we add another environment, we need two more conversions to the new environment. And if we add another platform, we need 3 more. And you can see where this is going. So we do things a little bit differently. We have our own intermediate format of the VM. And now we only need to be able to convert from each platform to the intermediate format and back. And this allows us to easily add platforms as well, because we already support all the previous platforms, right? So let's take a look at the failover test process. What's happening there? We have the mirror, we have the journal, and the checkpoint has been selected. So the first thing we do is we deploy the VM on the recovery side, and we have it locked. Why do we lock it? Because at this stage, we provide the view from the VRA, and we don't want you to move the VM around, right? It has to be tied to the same host as the VRA. And the VM has the view of the disk it uses. We also prevent applying the checkpoint at this point, right? Because we use this checkpoint and we use the data. Even if that data become outdated by the journal definition, we still can't apply to the mirror because we're actually using it for the view. And that's a very common mistake some clients are doing, keeping failover tests running for a lot of time, and then wondering why the VM starts syncing because the journal is actually full, and we cannot apply. We cannot free journal space. Okay, as the test is running, the protected VM may be doing more IOs, and we put these IOs in the journal as well. Everything good. However, the test VM may do its own IOs, right? Because you test stuff on the test VM. You do your own IOs. Where do we keep these, right? So for that purpose, we create another journal. This is called the Scratch journal. That's another bunch of disks that we create on the recovery site, and all the I/O that the test VM is doing are written to the Scratch journal. Once the test is over, we just throw away the Scratch journal, throw away the VM, and unlock the checkpoint, and everything is good, right? So failover live, that's what we're here for. This is the real thing. The protected site may be down at this time. However, it starts pretty much like failover test, right? So we start with a transaction. We create the VM. One thing that is different with failover live is that we ignore all sorts of minor problems. For example, if we created the VM, but we were not able to connect it to the network, we still go on. We do not want to roll back a failover live because of a minor failure, right? There are some failures we can be resilient to and go over them. We create the VM, we lock the VM, we create the draft journal. It's the same process, under the hood, exactly the same process as failover test. It's the same code. Once the customer approves of the state of the test VM, we can commit the failover, right? This is called failover commit. It can be done automatically, or it can be done through the GUI. When the customer declares this is a good failover, we need to take both journals, the Scratch journal and the real journal, and put them in the mirror, right? Until this ends, the VM is locked. Once this ends, we remove the lock. The VM, the mirror is actually becomes the VM's disk. And one last thing, if hopefully the protected site will come back again, we can use the original disk as the mirror. So this saves us a lot of synchronization time. Right, last one, that's move. So move is actually in the same way failover live is built on top of test, move is built on top of failover live. The only different things we do here is that we actually go and kill the VM on the protected side in an orderly way. And the reason we do that, we don't want the VM to do any IOs after the move started, right? So we kill the VM, we take a special checkpoint that is tagged. We know the VM is dead by the time we took that checkpoint, and that is the checkpoint we fail over to. And this is the way we get a consistent state on move. So a short recap, we were talking about view, which is a disk image as seen at a certain point of time. We are talking about the Scratch journal in use, failover test, failover, and move. And we were talking about promotion, the process of merging the journals into the mirror and actually ending the failover process, the recovery process. Okay, so we don't have any time for extras, unfortunately. So I just skip through. It's a little bit hard to skip through. Leave us some time for Q&A. Do we have time for Q&A?
Yeah.
Yep, okay.
If you want to stay, we have time. Sure.
All right. So, any questions? Yeah.
So, when the recovery VMs come up, they're going to come up as if the VM went kind of down, but the storage being pulled out from underneath it, right? So I know you guys have a tool to quiesce like SQL databases and that sort of thing, but like I know you guys don't promote it a lot. Like it's not necessary. It's not 100% needed. But like, are there certain use cases where it is needed, or do you just rely solely on just the efficiency of your checkpoints to do that, to get database consistency, really?
And
So database consistency
okay,
is
right.
my big question.
It's not different than any other consistency, right?
Yeah.
Because
Well,
if you got
sometimes a VM goes down, or a machine goes down hard with a database on it. You bring it up, and database is corrupt, right? So.
right, but this can happen for a regular database as well, right? If you were to shut down the physical database, I mean, recovery assumes that the VM has not been shut down in an orderly way.
Right.
Move does. This is how move is different.
Right, but so you haven't committed the writes from memory, as he said, to disk yet.
We do have support for what's the name of this?
You're saying we have VSS, we just don't
Yes.
Yeah.
quite as much.
All right.
Because to me, the penalty is you've got to really stop a lot of stuff for VSS to work. Our checkpoint system is nice to do it without that impact.
הוא יכול לתת זמן, מה שיש בזיכרון הוא איבד.
But you tend to run VSS like further.
ידוע. יותר טובים להעיף את הדיסק
כן?
הגדול.
חשבתי שזה לא עבד כל כך טוב כמו שזה.
אני מסכים, אנשים צריכים להכיר את החומר קודם,
כן.
זה היה גדול.